Hi, welcome to the Semantics lecture about characteristic functions. A function we've seen takes two sets and maps members of one to members of another. So how does that really connect with what we're doing with sets? We've seen that sets are really useful, especially when they're abstracted, because we can abstract a set to get us something corresponding to a property. So take for instance the word vowel. Imagine the orthographic vowels of English, and that would be the set A, E, I, O, U. We'll leave out Y because it's only a sometimes vowel, and we don't want part-time vowels. Now, we abstract over that set, we get X, the set of X, such that X is a vowel. So far, so good. How does that correspond to a function? Well, this is where the characteristic function comes in. Because for any property, there is at least one characteristic function, and it's going to be the function from whatever domain you have to exactly the objects in the set. So for instance with vowel, we will take a function that takes perhaps all the letters, and it will get us just A, E, I, O, and U. So how does it do that? Well, let's say we have a function, let's call it F, and we'll say that it maps from L, the set of letters, to the set of vowels. Right. Does that work? Well, how would that work? Well, if we take let's say A, B, C, D, E, and we'll skip the other letters for now. What does it map it to? Well, A will map to what? A? B will map to what? Well, it has to map to something. It has to map to one of these vowels. Well, how is that going to work? Well, the short answer is it's not. It doesn't make a lot of sense. So how do we get something that actually gets us the result that singles out the vowels but leaves the other letters alone? And that's where the characteristic function comes in. So the characteristic function works not by mapping to the set of vowels, but by mapping to one of two values. Everything in this set will map to one value, and everything out of that set will map to the other. So let's say we have a set of letters again in our function. What does it map to? Well, we usually use the standard 1 and 0, the binary distinction. So it maps to the set containing 1 and 0. And then the characteristic function works pretty simply then. If it's a vowel, it maps it to 1. If it's not a vowel, it maps it to 0. So in that case, it almost doesn't even matter what L is and what the domain is. It's going to be that function. Which function? Whatever function will do that. So in that case, we have A, B, C, D, E, and so on to Z. A, because A is a vowel, it will map to 1. B will map to 0. C will map to 0. D to 0. E to 1. So forth. And Z to 0. So, in essence, what you end up with, if you go down through through the whole alphabet, is the set of ordered pairs where some of them map to 1, some map to 0, and the ones that map to 1 are the vowels. And that's how you get a characteristic function to work. And this is going to lead us to our composition, because we'll see that we can turn the word vowel into this abstracted set by taking its meaning. So the meaning of vowel is the abstracted set. It's also this characteristic function, the function that maps, say, from letters to 1 or 0, and it maps it to 1 if it's a vowel. So we can write that out, right? Maps it from some domain to 1 or 0, such that F maps X to, missed a step. For any or all X in L, that is, whatever you take out of this L, out of this domain, you plug it into the function and you'll get 1 if and only if x is a val. And no matter how we write these characteristic functions, they'll all work the same way. And now we can say that the meaning of val is equivalent to that. And we'll tweak it just a little bit to mess with the domain, but we'll get to that. But essentially, it always works the same way. It's a function that maps from this domain L to this range, the set containing 1 or 0, such that for all members of the domain, f of x, so plugging the member into the function, will result in the answer 1 if and only if, and then you have this property. And this is the property, the same property that we saw in the abstracted set. So we saw the same property in the abstracted set. We also saw the same variable. And so, I'll put it here too. And so there's a tight link then between the characteristic function and the abstracted set. Essentially, the function will get you the set. So you can take anything you want, run it through this function, and you get the set. And that's the function that we're going to be using. So f equals L maps to 1, 0 for all x in L, f of x equals 1 if and only if x is a val. And the if and only if is important because it makes it a biconditional such that if x is not a val, if x does not have this property, it will map to 0. So everything in L will get mapped to 1 or 0. These get mapped to 1, everything else to 0. And that's the characteristic function. They all work that way. The exercise will have some more, and this will lead us right into composition.